We are going to look at a brief review of differentiation and integration of logarithmic and exponential functions. So at this point, I'm assuming you have learned all the derivatives and integrals of logarithmic and exponential functions. So the purpose of this video is to serve as just a review of all the main formulas you need to know. So the first formula is differentiating ln of u, where u is a function of x. So that could be ln of x squared, something like that. When I differentiate the natural log of u, where u is a function of x, that derivative just goes to u prime over u. In words, that means the derivative of the inside, where your inside is this u, over the original inside. So a very basic example would be if I want to differentiate ln x, well, x is the inside function, the derivative of x is 1, over the original inside is x. That is my u prime over u. So let's look at one basic example of that. So let's say I'm looking at the function y is equal to ln of the square root of 3x plus 2, and that is being multiplied by sine of x, all in the inside of that natural log. So all of this inside is grouped together. Now, if I treat this all as my u, which it is because that is the inside of the natural log, differentiating this is going to be kind of a pain. I have product rule between those two functions, chain rule on this function, and I don't really necessarily want to do that all to get that u prime before I put it over the original inside. So I can actually simplify this and make my life a little bit easier by expanding the natural log first using algebraic properties, then differentiate. So if I expand it, I have 1/2 ln of 3x plus 2 plus ln of sine of x. And now if I look through what's going to be required for me to differentiate, this is a simple u prime over u with a coefficient in front. There's nothing really complicated involved with that. I don't have any additional rules, which is good. So differentiating y prime would give me 1/2, and then my u prime over u would go to 3 over 3x plus 2 plus, and then I'm going to have to do u prime again, or u prime over u again for the ln of sine x, which will go to cosine x over sine x. And of course you could rewrite that as cotangent x, but for our purposes we just want to practice the actual formula, not simplifying. Now the next formula is going to be the integral of what we just looked at. So instead of having the derivative of natural log goes to u prime over u, now I'm dealing with the integral or antiderivative of du over u. And you have to realize du is the derivative of u, so that's like u prime. But of course the notation changes when we're looking at an integral. So instead of writing u prime, you now write du for notation. So if that's the integral or antiderivative of u prime over u, that's going to have to go back to the natural log. And then we have to put absolute value of u plus c. And that's because when I go back to the natural log, I have to actually restrict this domain right here. I can't have the natural log of a negative number that does not exist. And so I have to specify it's the absolute value of u, therefore my domain is restricted to all the possibilities that actually exist for that natural log. Now, typically most of these problems are going to be u substitution problems. So if I look at the one example I'm going to show you for this one, I have the integral of 3x squared plus 1 over x cubed plus x dx. So definitely going to be a u substitution problem because I have something pretty complicated looking with this fraction here. So in this case, my u is going to be x cubed plus x. That has the bigger degree, plus is the one on the bottom. And then du is the derivative of that u, which is 3x squared plus 1 dx. Notice I have all of the du in the numerator right here. So when I go back and substitute this in, I have the integral of du over u. And based on our formula, the integral of du over u goes back to the natural log of the absolute value of u plus c. And then the last step is just go back and plug in your u. So natural log absolute value of x cubed plus x plus c. So now I want to look at the derivatives of the exponential functions. So if I am differentiating e to a function of x, where I'm going to call that u, so u is a function of x, the derivative of e to the u just goes to e to the u times u prime. So basically in words, it's the original function times the derivative of the exponent, and that's it. So if I extend that a little bit, I could do something like e to the x. Well, the derivative of e to the x is just e to the x times the derivative of the exponent. Well, the derivative of x is 1, so it's just times 1, which we don't have to write, of course. So we'll look at one basic example of that. Let's say y is given as e to the cosine squared x. So my u is this cosine squared x. So when I differentiate, this is going to have to be chain rule again, because you have cosine squared has two different layers. So e to the u is the first part, times u prime. Well, that u prime is the derivative of cosine squared. That's the same thing as cosine x all being squared. So that requires chain rule, which means if I just kind of go to the side a little bit, make a little note over here, this is the same thing as cosine x quantity squared. So my outer layer is the 2, which I'm going to bring down in front, keep the inside, subtract 1 from the exponent for chain rule, times the derivative of the inside. Well, the derivative of cosine is negative sine. So all of this is y prime, which is the derivative of that e to the cosine squared x. Then, of course, the integration is very similar to that. So if the derivative of e to the u is e to the u times u prime, then the integral of e to the u du, remember your du kind of is like your u prime when you do u substitution, is just going to go back to e to the u plus c. Pretty much all of these problems are going to have to end up being a u substitution problem. Now if I had something basic like e to the x dx, then my u is x and the derivative of x is 1, so I don't need to do u sub on that one. It just goes back to e to the x plus c. So nothing fancy there. So let's look at an example of that. So let's say I have the integral of 5x e to the negative x squared dx. Definitely a u substitution problem because I see my integrand is pretty complicated looking. So I'm going to start off by making my u the exponent, since I only have one exponential function, which is negative x squared. And then the derivative of u is negative 2x dx. Comparing that to the original function, I have the x dx, but I don't have a negative 2 in there. So I can put in the negative 2 I need on the inside, but I have to balance it out with the x, or the reciprocal on the outside, so negative 1/2 on the outside. Now notice I have this random 5 that I don't actually need. So extra numbers that are being multiplied on the inside of the integrand, I can actually pull out in front instead. So if I rewrite this so it's a little bit clearer, I have negative 5/2 now out in front, times the integral of e to the u, and all the rest of that turns into du. Well, then that's just going to go back to negative 5/2 e to the u, which is negative x squared, plus c. And of course, you can always confirm your answer by differentiating it, and if you differentiate it, you should end up with that original 5x e to the negative x squared. Okay, we got a couple more left. So the next one is, what happens if we have a logarithmic function that doesn't have a base e? So it's not natural log anymore. It could be like log base 2, log base 10, whatever we want to look at. Just not log base e, which is the natural log. So let's say I want to differentiate log base a, where a is a constant, of u, where u again is a function of x. Well, the derivative of that is just going to go to u prime over u, but the only difference is because I have a base other than e, it's not like natural log, which went to u prime over u. I have to actually divide by the natural log of the base a in front. So it's u prime over ln a times u, all in the denominator. which means if I look at just the simplest example, which is log base a of x, well, my u is x, the derivative of x is 1, over the natural log of a times x for that u prime over u there. So we'll look at an example of this. So let's say that I'm looking at y is given as log base 3 of 10x squared. Then if I differentiate this, y prime would go to u prime, so my u is at 10x squared. The derivative of 10x squared is 20x over the natural log of the base, which is 3, times my u, which was 10x squared. And of course I could simplify this. I can reduce that to 2 over ln 3 times x. But if you're not required to simplify, you're perfectly fine leaving it with the first answer. So then what happens if we have an exponential that's not going to have a base of e, like we saw before with the e to the u? Instead, we have a constant raised to a function of x. So let's say I want to differentiate a constant number a raised to a function of x, which I'm going to call u again. Well, the derivative of e to the u just went to e to the u times u prime. Very similar here. It's going to be a to the u times u prime. The only difference is, because I'm dealing with a base other than e, now I have to actually put that into this formula. And so in front, you're going to multiply by the natural log of the base, which is a. So you have ln a times a to the u times u prime, which means if I had just a to the x, then I would have natural log of a times a to the x times the derivative of x, which is just 1, and I don't have to write that, of course. So here's an example of this one. Let's say I'm given y is equal to 2 to the 3x. Then my u is 3x, my a is 2. So when I differentiate, y prime goes to ln of the base, which is 2, times a to the u, so 2 to the 3x, times the u prime, which is 3. Now, if you want to put this together, make sure you're not combining that ln 2 with the 3. Because 2 is on the inside of the natural log, you can't put those together. The only way I could rewrite this, if I would like to, is I could do 3 ln 2 times 2 to the 3x, but that's not necessary, of course. Okay, last formula. This is if I'm dealing with the integration of an exponential with a base other than e. So the integral of a to the u du, where a is a constant, u is a function of x. So e to the u du just went back to e to the u plus c. Very similar here. It's still going to be a to the u, but because I have a base other than e, I have to divide by ln of a and then plus c. So with the derivative of a to the u, you multiply by ln a. But the antiderivative, you're going to divide by ln a, because remember, they're opposites of each other. They're inverses, so they do the opposite thing. Now, again, this is going to pretty much always be u substitution. So if I look at the integral of, let's say, 2 to the 7x dx, well then my u is going to be the exponent, which is 7x. Du is the derivative of 7x, which is 7 dx. So I'm missing the 7 on the inside, which means I have to divide by 7 on the outside. Then if I rewrite this, now in terms of u and du, then I'm going to have 1/7 integral of 2 is still there to the u, and then that 7 dx becomes du. And so then the integral of this would be 1/7 times a to the u, so 2 to the u, over ln of a, which is 2, plus c. And of course, you're going to have to actually plug in your u, so I'm going to go back up here and erase that u and rewrite it with what u is actually equal to, which is 7x. And of course, you could write this as one fraction, so I could say this is 2 to the 7x over 7 ln of 2 plus c is my antiderivative. So hopefully that gives you a better understanding of all the different formulas and a brief overview of all of them all at once. Thanks for watching.